my name is Ruben and I'll be talking about System Efficiency Index, SEI. COP is traditionally used as the KPI to analyze the performance of chillers and heat pumps. And here's a challenge regarding that. We have three systems with different COPs, and the question is which one we would choose. Now the COP is the capacity that we're getting, either cooling or heating. So the capacity that we get from the system compared to how much electrical power we put into the system. So the higher COP means we've got higher capacity we get from the system. So knowing that, we know that the higher COP means the better the system. If we put 1 kilowatt electrical power into the system and we get 1.5, compared to we put 1 kilowatt into the system and we get 2.2. If we were to choose between those two systems, we would choose the one with higher COP. Now, if we give a bit more information about these three systems so that we can compare them a bit better, we see that not all of them are running with the same refrigerant. The first two have R407C and the third one R134A. But more importantly, we see that the temperatures that they're performing at are very different from each other. The first system has evaporation at -6 and condensing temperature at 53, while the second one has evaporation at 2, condensing at 37, and the third one -3 to 34. Now, these temperatures are quite different, and it is normal that if we have a high temperature difference, for example -6 to 53, it is normal to have a lower COP compared to, let's say, system 2, where the temperatures are closer to each other. Now the question is, what would system 1 have as a COP if it were to operate in system 2's temperature conditions? It is a bit difficult to just look at the COP 1.5 and 2.2 and compare those systems, because the COP is dependent on the operating conditions. If we change 1 degree on the cold side, the COP would change 3 to 5%, and if we change 1 degree on the warm side, COP would change 2 to 4%. Going back to these three systems, if we were to increase the cold side about 8 degrees, then we would have quite a big change on the COP. In the same way, if we decrease the warm side to 37 degrees, the COP will increase. Now, this is a main challenge of the COP, that is dependent on the operating conditions. And we need to know these operating conditions so that we can tell if the COP is good or if the system can operate better, if there are other systems that operate better in the same conditions. Additional challenge is that systems never operate at design data. Now, manufacturers will include the design data, will include the COP at this design data, but the systems will never operate at those conditions. We also have seasonal KPIs, such as seasonal COP, and these are theoretical values that take into account the whole season, what we get out of the system during the whole year or during the whole winter. Now, this is good information by itself, but it will not help us to know the performance of the system, because the COP will change depending on the load, depending on the operating conditions, and the load itself will change depending on the operating conditions. So the existing benchmarks that we have, the COP, seasonal COP, are not easily understandable and they cannot be used to compare two systems. Because of that reason, we've developed System Efficiency Index, the SEI. It's a project sponsored by the Swedish Energy Agency in collaboration with RISE, Institute of Refrigeration in UK and VDMA in Germany. What this SEI is a tool to benchmark and compare. What we want to have here is that we need to know the performance which is independent of the operating conditions, independent of capacity and design. What we can do is to compare the performance of our system to the performance of a loss-free process. The loss-free process would operate in the same conditions that we have, so the comparison would be fair. How do we do that? We take the COP that we're measuring, so we're still using the COP, but we compare it to the Carnot COP. And the Carnot COP is basically the COP of a loss-free system. And how we calculate the Carnot COP is that we take the cold reference and the warm reference. This will give us the operating condition of our system. And we would just say that the Carnot COP, the loss-free process, is operating in the same conditions. So we need to define the cold reference and warm reference temperatures. These are the operating conditions of our system. So for a water-cooled chiller or ground source heat pump, we would take the average value of the secondary cold in and out. So in this case, it will be the chilled water in and out, and we would take the average value. This would give us the cold reference temperature. We know our operating conditions. We know how cold water we would like to have, and we know what is cooling our system. And we can say that these are our operating conditions, and this will be the operating conditions of a loss-free system that we want to compare to. And what if we have free-blowing heat exchangers, for example, air-cooled condenser? And in that case, we would take the incoming air plus 5 degrees. The incoming air is the most important in this case when we have air-cooled condensers, and it will be our benchmark. For direct expansion with several evaporators, this would be the case for supermarkets. So we would take the lowest set points. For example, in a medium temperature, this might be 2 or 3 degrees. So we would take this lowest set point and do -5. This is how we define the reference temperatures. And going back to our equation here, we know the reference temperature, we know our operating conditions, so we can calculate the COP of a loss-free system. And this is our system without any losses. It is 100% operating without any losses. And our system, we know how it operates because we're measuring the COP. So we can compare our system to a loss-free system. And what we get in that case is the System Efficiency Index, the SEI. Now, this is represented from 0 to 100%. 100% is the performance of a loss-free system. There's no losses, it's operating at 100%. Now, the best systems that we're looking at are operating between 50 and 55% compared to a loss-free system. And we measure this by measuring the COP of our system and comparing it to a COP of a loss-free system. The SEI, the System Efficiency Index, can be further divided into different categories. The 4 main categories are the refrigerant cycle, the compressor, evaporator, and condenser. These are always measured in our basic system. Further, we can measure as well the pressure drop, power of the pumps and fans, and heat exchange with the environment. Each of these factors will reduce the performance of our system. And we can measure that by measuring the pressure drop and the power going into the auxiliary systems. But the main four parts are the refrigerant cycle, the compressor, condenser, and evaporator. Now, what is the cycle? It is the refrigeration cycle, and this is affected by the subcool, superheat, and the refrigerant itself. So when we have higher subcool, then the performance of our system will increase. The compressor is the isentropic efficiency of the compressor. And for condenser and evaporator, we are checking how efficient is the heat exchange. If you notice, the refrigerant cycle has more than 100%. And this will be the case for systems with economizers. Now, those systems will operate better than systems without economizers. And our loss-free process is one without economizer. So compared to our loss-free system, the economizer system might have efficiency higher than 100%. For the condenser and evaporator, we're checking how efficient is the heat exchange. So we're comparing to infinitely big condensers and evaporators, where the heat exchange is done with 100% efficiency. The representation of each of these efficiencies includes also all the KPIs related to these efficiency. Now, for the refrigerant cycle, we talked about the superheat and the subcool. As we increase the subcool, we will have higher performance. The economizer will give us that opportunity to increase the subcool and have a higher performance. The compressor efficiency is the isentropic efficiency. And here we're looking at the pressure ratio between the low pressure and the high pressure. We have the discharge temperature. The superheat will affect the discharge temperature. As we increase the superheat, it will be more difficult for the compressor and it will operate with lower performance. We also have the power input that goes into the compressor. Many compressor types will operate with lower efficiency when they're running on part load. They will have a full load efficiency which is much higher than the one in the part load, and we need to take that into account when checking the compressor efficiency. Checking the condenser efficiency, we're looking at the capacity that we're getting from the condenser. We're looking at the water in and out of the condenser, and we're looking at the condensing temperature. Mostly here we will look at the difference between the condensing temperature and water exiting the condenser. Ideally, this approach temperature would be as low as possible. We would like to have a condensing temperature which is as close as possible to the water going out of the condenser. The condenser efficiency is also affected by the water in and out and by the flow of this water going into the condenser. If we have a too high flow, then the heat exchange will not happen as good as possible. So having the flow on the secondary side is important and will show issues on the secondary side. The equivalent on the evaporator, we're checking on the water in and out, the flow of this water, the evaporation temperature, and the difference between the evaporation temperature and the water exiting the evaporator. In the same way, we would like to have this difference, this approach temperature, to be as low as possible. In that case, we will have a high evaporator efficiency. Now, we've been talking about the main 4 components of the SEI. In that case, we have the compressor, condenser, evaporator, and expansion valve, and this is represented by SEI 1. If we include further boundary, then we have SEI 2. And in this case, we have pumps and fans. So we can measure the electrical power going into this pump and fan so that we know how much they affect our system. We can also measure the heat that is generated by these pumps and that is going into our system. And that will give us a better accuracy on SEI 2, which includes a bigger boundary of our system. So to conclude, what are the system efficiency index benefits? It is intuitive. We're comparing to a loss-free system. We have a 100% efficient system, and we're comparing our measured system to that 100% efficient system. It is practical to use. We can easily compare 2 systems and see which one is performing better. We can see if there are issues in our system by looking at the SEI. If it's in the orange, yellow, red zones, then we know that the performance can be better. And we can dive deeper into the analysis, looking at the 4 sub-efficiencies: the cycle, compressor, evaporator, and condenser. And there we can check which part is affecting the performance of our system. Now the SEI, the System Efficiency Index, is published in a report, and the link is available in here. Thank you.